talk about this.
Thanks, Russell. I'm really happy to be here again. I was here last fall. It was really exciting. So today what I'm going to do is I'm going to just tell you a little bit about what I've been doing and what the community has been doing on hardness for easy problems, whatever that is. I'll explain this in a little while. And it's not going to be a technical talk. It's just going to be an introduction to the topic, and I'll go into details in the other talks of this boot camp later on. Okay? So, all right, so what are we talking about? How can easy problems be hard? So let's start with a little cartoon. Okay, so this is the real world, and let's discuss hard problems. So we have a scientist here, and the scientist has done a lot of work. They've collected a lot of data, and they say, okay, I've got all my data now. I need to analyze it, and let's learn something about it. And I have some algorithmic problem in mind, and I really want to solve it, but I'm stuck, and I'm not sure what to do. I haven't found any good algorithms. So then the scientist goes and finds a computer scientist. Okay, this is the best cartoon I could find online. I think this is how the world sees us, apparently. Okay, so yeah, the computer scientist looks at the problem and says, well, okay, I'm sorry to say this is an NP-hard problem. If you would resolve it on all instances with a very fast algorithm, then you would solve a very, very hard math problem, okay, computer science and math. And so the scientist says, oh, whew, okay, everything I tried didn't work, but there's a reason why. I feel better. I'm going to use my heuristics, and I'll be okay. Sometimes they work, sometimes they won't, but probably the best algorithm has this problem too. Okay, so fine. So this is some solution to the hard problems. Now the scientist has a different problem now, which they present to the computer scientist, and the computer scientist says, great news, your problem is in polynomial time. I have a quadratic time algorithm for it. Okay, so this is wonderful news from our perspective, but then the scientist says, but now, I have this huge data, and n is actually enormous, so what should I do? N squared, maybe for small n is really nice, but my n is actually really huge. Can't you find me a linear time algorithm? I would be much happier with a linear time algorithm. And then the scientist says, I don't know. I tried to find a linear time algorithm, but I couldn't. And why aren't you happy with n squared? N squared is perfectly fine. But yeah. I don't have a good answer for you. And then the scientist says, well, should I wait for you to find a linear time algorithm? Can't you give me some reasons why you don't have one? I mean, isn't that your job? Okay. And so, yeah, so what do we do here? We want to have a similar answer as with the hard problems as with the easy problems. And yeah, so this is what we're kind of trying to do here. Okay, so let's have a little aside about things we all know. Polynomial time for us can mean efficient or easy, but that's not because we think all polynomials are nice. It's because of other technical reasons. Because when you compose two polynomial time algorithms, you get a polynomial time algorithm. You can also have model independence and things like this. But of course, n to the 100 is not considered efficient, and even n squared can also be suboptimal for some applications. So how do we explain when we are stuck on improving on problems that have some n squared or n cubed type solution, but for some reason we can't improve it? So usually the solution is something simple. Sometimes it just follows from the definition, and yet getting something better seems to require some very different techniques. Okay, so in this talk, I'll talk about easy problems, and by easy here I'll mean n squared time, where n is the size of the input. Okay. What do we know about n squared time problems? We have really, really fast algorithms for a lot of interesting problems, faster than n squared time. We have all these classical linear time algorithms for, strongly connected components, spanning tree, a lot of problems on graphs, and also other things like sorting and so on. but also we have really sophisticated algorithms that seem to give us really, really nice techniques to solve more difficult-looking problems like max flow, matching, min-cost flow, and so on. And we also have this area of sublinear algorithms, property testing, and so on. And sometimes we can solve problems really, really, really fast. So we have developed a lot of these techniques, and this is really, really great news. Okay, a lot of problems are in close to linear time, or a lot of problems we know we really want to solve in practice, we can actually solve. Now there's also the bad news. We have a lot of problems that have some simple algorithm. That's probably the first algorithm that people came up with when they defined the problem, and usually it's some n to the c time algorithm. Okay, but then after this algorithm, there was no improvements for many decades, maybe very tiny improvements like logarithmic. And so here I'll give you a few very interesting examples of such problems. So here's a problem in computational geometry. You're given n points in the plane, and I want to know if any 3 of them lie on a line. So in other words, are these points in general position? And whenever you want to solve a computational geometry problem, you probably want to first do this. Okay? And there is an n-squared time algorithm to solve this problem. For example, for every pair of points, you could compute the slope and the intersect. And then every line is defined by these 2 quantities. And you just have to find whether there's a collision. So whether the 2 lines defined by 2 pairs of points, I have the same line. So you can do this. Now, this has been known for a long time. So n squared is known, but no significantly better than n squared. So no n to the 1.999 algorithm is known for this problem. Okay, so this is computational geometry. And there's many other problems in the area that have this issue. So there's also these string matching problems. Things like edit distance or sequence alignment and longest common subsequence and so on. So usually what you're given is 2 sequences and you want to know how similar they are. So here, let's say you're given 2 DNA strings and you just want to know what is a similarity, and then there's many different notions of similarity. So as I mentioned, there's the longest common subsequence, which I'll define formally on the next slide, but we teach it in our algorithms courses. There's a slightly more sophisticated notion called edit distance. There's local alignment. There's other for shade distance and so on. You can define a lot of different notions of sequence alignment, and they're all solved in practice. So in order to figure out how close these sequences are. And these problems also have applications to things like spell checking and computing the difference of 2 texts and so on. So here's the simplest version of the problem. You're given 2 strings over some finite alphabet, let's say the alphabet of length 4, and you want to find a subsequence of both the strings that's of maximum length. So a subsequence can skip letters, but it has to be in the same order as the letter as the sequence itself. Okay, so here the blue, I can put gaps because I'm skipping this letter G, and the blue letters form the longest common subsequence of these 2 sequences. And of course, as I mentioned, it has a lot of applications. It also has an n-squared time algorithm. It's a dynamic programming algorithm. This is the example that I teach in my algorithms course. And it's also very practically motivated to solve daily on huge strings. Now, I looked this up. It's typically not solved on the whole human genome, but let's be a little loose here and say that if you want to do it on the whole genome, it will have a few billion base pairs. And so if you run the classical dynamic programming algorithm that would take you a little bit too long. So, all right, and again, I really want to know, why isn't there a linear time algorithm? Why can't we even do n to the 1.99? And this is more than just a practical motivation. It's sort of an intellectual question. Why? It would be nice to know. Okay, so so this was geometry and string matching, and now for graph problems, we also have such examples. So here's one of the simplest graph parameters. The diameter is the largest distance in a graph. And suppose I even give you a very sparse graph. You have n nodes and order n edges, and I want you to compute the diameter. And maybe even I tell you approximate the diameter. Give me an approximation. How fast can you do it? The simplest algorithm is to compute all the pairwise distances and find the maximum one. But this will inherently require n squared time because there's n squared pairs. And unfortunately, we don't have a significantly faster algorithm than that. So even just approximating the diameter better than like a 3/2 approximation seems to require n squared time. And I will discuss this in a later talk. Actually being able to solve the diameter faster implies things for satisfiability and many other problems. So, okay, so we have a lot of these examples in just 3 areas of computer science, but there's many other areas where such problems pop up, and we would like to know what's going on. So so n squared is not anything special. You could say things about other runtimes. So, for example, there's no n to the 1.5 minus epsilon time algorithms for problems in dense graphs. So here n is the number of nodes squared. So we have n cubed, the little n cubed time algorithms, which translates to big N to the 1.5. Big N is the input size. And so things like all pair shortest paths, diameter, radius, median, lots of shortest paths related problems in dense graphs don't seem to have faster than n to the 1.5 algorithms. And so, again, we have this issue. We have a class of problems, a lot of problems, for which there's a polynomial time algorithm that's basically the simplest one you could come up with, and we don't know how to beat it. Okay. Good. Are we stuck for the same reason? So this is one question. Are all problems that we're stuck on difficult because of the same reason? Is it because we don't have the techniques? Is one big technique just going to solve all of them? And how would we address this? So in order to address it, let's just take a step back and think about how we addressed it for the hard problems. And here's a canonical hard problem. It's KSAT. You have n variables and m clauses, and every clause is of the form an OR of k literals, where each literal is a variable or its negation. And you want to know if there's some Boolean assignments to the variables that makes this formula true. So there's a trivial 2 to the n algorithm of times polynomial. For this problem, you try all possible 2 to the n assignments, plug them in, and check if the formula is satisfiable. Now, if k is a constant, you can actually do a little better. So you can do 2 to the n minus some other constant times n over k times poly n time. And unfortunately, as k grows, this becomes essentially 2 to the n. Okay? So the best known algorithm for CNF SAT in general runs in roughly 2 to the n time. And but this is not really why the reason we give for why KSAT is hard. The reason we give is, well, KSAT is NP complete, and this is why we think it's hard. Now, what does that really entail? It just says we believe it's hard because if it had a really fast algorithm, let's say poly n time, then all problems in NP have such an algorithm. So the reason why we think KSAT is hard is because it is so expressive, it captures all problems in NP. So All right, so we want something like this for these easy problems. We want to say the reason why we think they're hard is because, well, they capture a lot of other problems, the hardness for a lot of other problems. Okay? Okay. And the way we did this for the hard problems is we used polynomial reductions. Now, if we wanted to do something like this for the easy problems, we can't do this exactly. So we have to be a little bit more careful about the runtime of our reductions. So I will tell you a little bit about that in a moment. Okay, so here's one approach you could try. So the first thing we do is we're going to identify some key hard problems, things we really, really believe are hard, things that we believe that we cannot improve on their classical algorithm or brute force algorithm. Okay? And then what we'll do, we'll try to reduce these problems to all other hopefully all other hard, easy problems. Okay? It's a little vague, but I'll get into it. And then hopefully we'll sort of form equivalence classes. And if we believe that all the problems on which we're stuck on for the same reason, then we should really have only one equivalence class or something like that. But that's not where we're at right now. And in the end, one of the major goals is sort of understand what polynomial time looks like. So far, we've had some success in understanding it. So we had some circuit classes and so on, but I really want to understand it in terms of running time. So I want to know where things lie. Okay, so let's get into it. So first I'm going to tell you the key hard problems we've looked at, and then I'll talk about what the reductions look like, and maybe I'll mention a little bit about equivalence classes and so on. Okay, what are the hard problems? Let's start with CNF SAT. So we said, okay, it's NP complete. But actually, it's conjectured to be really, really hard. And there's two popular conjectures about SAT. The first one is that 3 SAT requires exponential time, so 2 to the delta n time for some constant delta. And the other, even stronger conjecture is that for every epsilon, there's some constant k such that k SAT on n variables and m clauses cannot be solved in 2 to the n minus epsilon n time. So if you set epsilon to go to 0, essentially k SAT for some k can be solved in 2 to the n time. Okay, so strong ETH and ETH. So one thing we could do is we could try to take k SAT for growing k, reduce it with some fancy reduction to a bunch of problems, and say, well, we believe these problems are difficult to improve on their classical solution because if we did that, then this conjecture that a lot of people seem to believe would be false. Now, some people don't believe this conjecture, but then you could say, well, these reductions are ways to attack it. You know, we're reducing them to easy problems, so you should be solving the easy problems to refute the conjecture. So there's 2 ways to look at it. Okay, so this is one of the hard problems we looked at. Here's 3 others. It's not hard? Okay. There's 3 more problems we can play. So here's a problem called threesome. It's been studied to death, basically. So here you're given a set of n integers, and you want to know if 3 of the integers in the set sum to 0. I'll just define the problems and I'll go into them. There's a second one. It's orthogonal vectors. Now, this one, you're given n vectors in over a small dimension, d. It's logarithmic, let's say. And you want to know if 2 of these vectors are orthogonal. Now, the vectors themselves have values 0 and 1. So really what we're asking is, are there 2 vectors such that whenever one of them is 1, the other one is 0? So just want to point out, it seems like a not too difficult problem, but it's kind of hard. Okay. And the third one, we're given a weighted graph. You want to find all the distances. So this is all pair shortest paths. I think everyone knows it. Okay. So now what I'll do is I'll go through each of these problems. I'll tell you a little bit about the prior work, and then I'll tell you a little bit about what we've been able to show. Okay, so threesome, again, n integers, you want to check whether three of them sum to 0. There's an easy n squared time algorithm. Easy. And n squared log n is actually very easy. What you do is you take every pair of integers in the set and check whether the negative is also in the set. And you can shave off another log. So then in 2005, Poran, Dimain, and Petrashku showed that you can actually shave 2 more log factors. And whenever the set of numbers are integers, you can get an n squared over log squared n time algorithm. Now, if the set of numbers are real numbers, then an even more recent result showed that even in that case, you can do a little bit better than n squared time. You get n squared over log n. Okay, so really n squared is not the right answer, but
Is that like a circuit, algebraic circuit model?
the real ones, or so this one is in the word RAM, this one is in the real RAM, and yeah, so the model matters here. Okay, so here from now on, I'll talk about threesome over the integers. This allows us to do some other tricks like hashing and so on. Okay. And there's a folklore result that says that if we're over the integers, we can just reduce the general case to the case when the integers are between minus n cubed and n cubed. And then there's this conjecture that has been formulated in many, many papers, which says the threesome on a set of n integers that lie in this range requires n squared minus little o of 1 time. So this is the very famous conjecture. It has been used to show that many, many problems probably require n squared time. There was a term that's used, n squared hard, which is very strange, but in computational geometry, they use it to mean that you can reduce threesome to your problem of interest. So there's a huge body of literature that where people have explored using this conjecture as a basis for hardness.
Excuse me.
Yeah.
Can you give some hints about this folklore result? Which is the idea?
You can do a randomized reduction. You can pick a random prime and so on. For example, you could do that. I'll let you know later. Okay. There's a few ways to do it. Okay. All right. So there's threesome, and then orthogonal vectors. What's orthogonal vectors? Again, you have n vectors over small dimension, and you want to know if 2 of them are orthogonal. There's an easy n squared log n times solution. You try all pairs of vectors, compute their inner product, and you check if it's 0. Now, the best known algorithm, okay, it's a little difficult to read, but what you should notice is when the dimension is some constant times log n, you get a little bit of an improvement depending on the constant in front of the log. So it's always better than quadratic for every constant, but as the constant goes to infinity, it goes to quadratic time. So this is a very recent result, and it's the best known result for the problem. Unfortunately, even that result uses very, very sophisticated machinery, and it was still not enough to improve on the quadratic runtime substantially. So then there's this conjecture that, again, has been formulated over and over, which says that this problem also requires n to the 2 minus little o of 1 time. Again, we have to specify the model and so on. Yes.
Don't you mean for instead of d equal big O, d equal little omega?
Where? Sorry.
In the statement of the problem.
Oh, yeah. For the actual conjecture, you need a little omega. Yeah. Yes. Exactly. Thank you. So for the conjecture, I have to change the problem. So you can think of d as log squared then. I was just trying to save some space. Okay. So, all right. So let's say the dimension is log squared then. That'll be fine. Thanks. Now, there's this result from 2004 by Ryan, and he showed that if you believe the strong exponential time hypothesis, then you should also believe this orthogonal vectors conjecture, because he reduced k-SAT for OK to this orthogonal vectors problem. And if you could improve on n squared time substantially, then you would also improve on 2 to the n substantially. So I will actually prove this to you in a little bit. So hang on. Okay. So this is that one. And the third problem is all pairs shortest paths. So it's a classical problem. It has very, very, very long history. Here's a little slice of the history. So before 1976, it wasn't known whether the n cubed runtime can be improved. N cubed you can get by doing the Floyd-Warshau algorithm, for example. And then Friedman noticed you can actually improve it on it a little bit. You get a log to the 1 cubed and 1 over 3n improvement and so on. And this was more and more log factors were shaved up until 2012. And then Ryan used some very different machinery here to improve on all log factors. So now you can get a 2 to the squared log n improvement over n cubed. Unfortunately, this is still not a polynomial improvement, so we don't know whether there is a better than n to the 3 minus epsilon time algorithm for any epsilon. And then there's this conjecture that all pair shortest paths, whenever the integers are on order log n bits, it requires n cubed minus little over 1 time. And all of these conjectures are about the word RAM, just so we're clear. So now we've identified some key problems, and you can add more and more to the list. And now what we want to do is take these problems that we really, really believe are difficult because people from a lot of sub-areas of computer science have tried to solve them and haven't succeeded so far. And we want to reduce them to our favorite problems, to diameter problem, to let's say longest common subsequence, edit distance, whatever you want. Any favorite problem that you have, we want to reduce one of these to them. Okay, but how do we do these reductions? So we coined this term fine-grained reduction, which is in line with the title of this program. Okay, so let's start with 2 problems, A and B. Let's say they have some natural algorithms, and the algorithm for problem A runs in little o of a time, and the algorithm for problem B runs in little b of n time. And now we say that A is reducible to B if we're improving on this natural algorithm for B in a substantial way also implies that you beat the natural algorithm for A this time. So here's some way to do it, which I think is the natural way. So what you do is you take an instance of a problem A. In order to reduce it to problem B, you have a reduction, which is an algorithm that runs a little a of n to the 1 minus delta time. Delta is some constant, as close to 0 as possible. Someone gives you an epsilon, and for every epsilon give a delta, okay? And then you produce instances of B. It doesn't have to be one instance. You can have as many instances as you want. But the sizes of these instances obey this inequality here. What does this inequality say? It says that let's take the sizes of these instances here to be n1, n2, n3, and so on. And then when you run an algorithm of runtime B of n1 and B of n2 and B of n whatever, and if you improve on B of n by a polynomial, by a constant factor in the exponent, so then the total runtime of the algorithm will be the sum of B of n1 to the 1 minus epsilon, B of n2 to the 1 minus epsilon, and so on, plus the runtime of the reduction, which is A of n to the 1 minus delta. And when you sum all these two up, you get an algorithm for A of the runtime A of n to the 1 minus delta. So all I'm saying is that if you get an improvement for problem B with an epsilon improvement in the exponent, then this translates into a delta in the exponent improvement for problem A. Okay, so we're not actually saying that the runtimes are preserved. So this is the important point. The runtimes are not necessarily preserved, but what you do preserve is the existence of a substantial improvement over the classical runtime, the natural runtime. So sometimes, usually this natural algorithm is some brute force algorithm, but sometimes it's a dynamic programming algorithm and so on. Okay. And the thing is, we focus on the exponents because when A and B are polynomials, then this is improving over the polynomial. If it's n cubed, improving on n cubed. If it's n squared, improving on n squared, and so on. And using such a reduction, we can form these equivalences that talk about improving over exhaustive search or improving over the natural runtime of problems. All right. Yes?
Why are we focusing on the naive runtimes? I mean...
Well, I'm a little vague here. So we can, for a lot of problems, we do have some natural way to solve them in a brute force way. For example, think about multiplying two matrices. The brute force way is you follow the definition, you get an n cubed time runtime. Okay, so for some problems, it's not as natural. So think about shortest path. Just going through all possible paths, that's too long. But there's a very natural algorithm that doesn't go through all possible paths, but it's in a clever way, it actually goes through the optimal paths. So this is also a natural algorithm. So this is why I'm being a little vague. But it turns out that often these natural algorithms hide the brute force algorithm in them for maybe a simpler problem. And there's some exhaustive search going on.
So do you allow adaptive reductions?
Yeah. Here I'm not. I haven't done that. But yes. Yeah, you can do this. Huh?
The way it's written, it doesn't rule out.
Yeah, I know this way is written, but I mean, you could get the same properties allowing adaptive reduction.
Oh, it doesn't rule out an adaptive.
Oh, it doesn't. Oh, okay.
Just the way the picture looks, it looks like a non-adaptive reduction.
Yeah, you can do this one first, and you can change the order. Yeah. It's.
It wasn't clear whether you needed the answers.
You actually need adaptive reductions for these equivalences.
Will you see tomorrow? Okay. We have adaptive reduction. Actually, it's important. Yeah. It's not. We don't always need them, but sometimes actually it's important to have them. Yeah. So you can. The way you get this reduction, how you pick this one depends on this one, and so on. So it is a little adaptive, but this is the basic idea. Okay. So we're trying to build some theory of hardness for polynomial time, but we also want to relate problems maybe outside of polynomial time to problems in polynomial time. And in general, we're trying to relate problems to each other depending on what we believe is a true runtime. Okay, so here's again what we were talking about. So I talked about the key hard problems, the reductions, and now I'll discuss a little bit about the equivalence classes. So, okay, there's a little map of some of the things we know. So I'm going to try to go through it a little bit. So here's the three-sum problem again, and integers, you want to check if three of them sum to 0. In the 90s, there was a huge burst, like a golden age of this approach, where you take three-sum, reduce it to your favorite problem in computational geometry that seems to require n squared time, and then say, well, we believe that n squared time is the real answer because we really don't think we can improve on three-sum substantially. So there was a really, really huge body of literature here, and it was confined to computational geometry. Okay? And then recently we've been taking three-sum and also reducing it to problems outside of computational geometry. There's also a jump in the way reductions work. In the recent literature, we've been using some hashing techniques and things like this that actually manipulate the integers in question. In the previous work, this wasn't done, so it would even work. The reductions would often even work, even assuming that threesomes for real numbers requires n squared times. So maybe some of these are stronger, but these use more interesting techniques, and you can prove more and more results. Okay, so, and this is really a growing body of literature. So now, all pair shortest paths, different problems. We know how to reduce all pair shortest paths too. For example, the following problems in dense graphs. Radius, so the radius is just like the diameter, except now for every node you take the largest distance from it and you take the node that minimizes that. So a node that achieves the radius is sort of a central node in the graph. So in dense graphs, the radius problem is actually equivalent to all pair shortest paths. Median, betweenness, negative triangle, which are defined as second shortest path. So what's second shortest path? You're given a graph. We know how to compute the shortest path between two nodes, S and T. But now I tell you, besides the shortest path, compute the second shortest path, the second in the list. And we make the restriction it has to be simple, because I don't know. And now, if we do that, all of a sudden, instead of taking linear time, it starts taking n cubed time. And it turns out this is because it's equivalent to all pair shortest paths. So these two problems and many more, Ryan and I had a paper in 2010 that showed these reductions that followed in the way that I had on the slide. And what they say, the equivalence is that if you get an n to the 3 minus epsilon algorithm for any of these problems, then you get an n to the 3 minus delta algorithm, maybe a different delta for all the others. So, okay. So we have all these problems in graphs that seem to be equivalent to all pair shortest paths. Yes?
All of these are on graphs. Is there a similar development for digraphs?
Oh, yes. By graphs, I mean directed graphs and undirected. In fact, these problems, even in both directed and undirected, they seem to be equivalent. Right. So we have this growing body of equivalences. Note that for threesome, there's no equivalence. This is just one direction. There's very few problems that are known to be actually equivalent to threesome. Orthogonal vectors, the problem where you're given you're given n vectors, you want to know if two of them are orthogonal. We have reductions from that problem to a bunch of problems in sparse graphs and a bunch of problems in string matching or sequence alignment and so on. So for example, if you have an n to the 2 minus epsilon prime algorithm for any of these problems, longest common subsequence, edit distance, Frechet distance, and diameter and so on, then orthogonal vectors also has a subquadratic time algorithm. So we have orthogonal. If you believe that orthogonal vectors is hard, then a lot of problems in different parts of computer science would also be quadratic hard or whatever. They will require n squared time essentially. Okay. So again, there's very few equivalences, maybe one or two, between this problem and others, but it implies hardness for many. Now, it turns out if you look at dynamic graph problems, so here, so what's a dynamic problem? Usually what we do is we want to compute some function, but now someone tells you this bit of the input changed, or if you have a graph, an edge disappeared or an edge appeared, and now you want to update the function. Okay, so that's a dynamic problem. The question there is, how fast can the updates be done while being able to support queries about the value of the function? So think about, let's say I have a directed graph and I want to maintain the strongly connected components or their number, and now someone says this edge is no longer there. Now you want to know that the number of strongly connected components change, and what is that number? So it turns out that every one of these problems can be reduced to some subset of dynamic problems, and some dynamic problems can solve all of these three problems. So you can explain the hardness of many dynamic problems by focusing just on these three core problems. Okay, as I mentioned, you can take k-SAT for growing k, so CNF SAT if you say, and reduce it to orthogonal vectors, which means that any of these problems and the ones here would be, if you get a substantially improved algorithm for them, then the strong exponential time hypothesis would be false. So I'll show you this in a second. So this is most of what we know. There's a few other things that I'll mention later. But are there any questions here? Yeah.
The approach we're kind of doing here isn't like trying to create like some quadratic complete problem. It's more like maybe reduce like strong exponential time hypothesis to one of these and then reduce them to other things too.
Well, okay, so ideally I would like to say that all these problems are equivalent. Okay, that's ideally what I want to say. Sometimes we don't know how to do it, so then we only get reductions in some. But we get proving some relationships about problems. And sometimes actually what you can do is you can build, just as I'll show you in a second, the relationships will be for different runtimes. So it's
But so far, so like Ryan used a few days ago, used the distinction between like classical complexity tends to be machine-based. You organize problems by machine model, and this seems fine-grained complexity seems to be a problem-centered approach.
exactly, yes. This is problem-centered.
Getting at.
Exactly. Thanks, Russell. So what I'll do now is I'll present Ryan's reduction from 2004, and after you understand this reduction, then we can often just forget about CNF SAT and just focus on orthogonal vectors. It's not always the case. Sometimes you can get reductions that are not from orthogonal. You can't get a reduction from orthogonal vectors, but you can from CNF SAT or from, with constant clause width. But most of the reductions follow from this. Okay, so what are we going to prove? We're going to take some, for any k, we take a k-CNF. It will have n variables and order n clauses. We can assume this by the sparsification lemma, and there should be an f here. I don't know why it's cutting off. But okay, so, and then what we'll do, we'll convert it to an instance of orthogonal vectors, so that if you can solve orthogonal vectors in less than n squared time, then the original formula can be solved faster than 2 to the n. Okay, so what we do is we take the variables, we split them arbitrarily into two sets of n over 2 variables each. Then, for every partial assignment of v1 and v2, we're going to create a vector. We'll call the vector v1 phi, this j corresponds to whether it's v1 or v2, and phi is the partial assignment. Okay. Now what we'll do is we'll forget about this for a second. This part over here will just be, we'll have a coordinate for every clause, and for clause j, we'll put a 0 if the partial assignment actually satisfies this clause, and we'll put 1 otherwise. Now this portion over here, it would just sort of say which partial assignment, to V1 or to V2, are we talking about? If it's to V1, we'll put a 0, 1, and if it's to V2, we'll put a 1, 0. So this basically means that if we're talking about two partial assignments to variables to only V1 or to only V2, then the two vectors will not be orthogonal because they'll both have a 1 in this position or both have a 1 in this position. So any two vectors that are orthogonal actually will correspond to partial assignment of the first half of the variables and a partial assignment of the second half. Okay, and then once we have that, similarly to the partial assignments of the variables of V2, we'll put a 0 if the partial assignment satisfies the clause and 1 otherwise. Now we look at two vectors of this form, and we can see that the only way for them to be orthogonal is whenever this one has a 1, this one has to have a 0. So this means that whenever this partial assignment does not satisfy this clause, this one has to satisfy it. Here it is again. So the only way, so a partial assignment phi and a partial assignment psi, this one to the first half of the variables, this one to the second half, form two vectors that are orthogonal if and only if together the concatenation of the two partial assignments satisfy the formula. Okay, so, and this completes the reduction. Yeah?
Couldn't you have an assignment which satisfies a clause in the bottom one and in the top one?
Yes. Yeah, and then both of them will be 0, and then it will contribute nothing to the inner product.
Ah, yeah.
So that's why I picked 0 there. Yeah. So if both partial assignments satisfy the clause, both of them will be 0 in that coordinate, so it won't contribute anything. And if one of them satisfies it and the other one doesn't, it will have a 1 times 0, and it will be okay. And the only time when they're orthogonal is when there's some coordinate in which both of them are 1, but that means that neither of them satisfy it. So that's the claim. Now, what's the size? What is the reduction size? The number of vectors we get is roughly 2 to the n over 2. It's 2 times that. The dimension is basically the number of clauses plus 2, which is order n by our sparsification lemma. And this little n is now log of big N, because the number of vectors is 2 to the n over 2. And so we get that if you can solve the orthogonal vectors problem for this instance in big N to the 2 minus delta time, you get a better than 2 to the n algorithm for the original formula. Now, when you actually do the proof, you have to care, because strong ETH actually says for every epsilon there exists a case such that the runtime is 2 to the 1 minus epsilon n times. So you have to be a little bit more careful how you do this, but this is essentially the proof. So now this is a split and list technique, and most reductions either use orthogonal vectors now as their base case for proving hardness from strong ETH, or if they don't do that, then they take an instance of KCNF and apply techniques that's very similar to this. So maybe you don't split the variables into 2 sets, maybe you split them into 3 sets, and then you do the partial assignments. But usually it's something like this. All right, so we're back to this picture. Now we know this portion over here. And what else I'm going to say? Now, these are kind of, maybe we think these are kind of believable conjectures. So we can ask, what other conjectures can we make? So here's another one that appears in the literature. It's a conjecture about Boolean matrix multiplication. So you're given 2 Boolean matrices A and B, and you want to compute their product, which is defined as an OR of ANDs. Okay, and you can compute it in n to the omega time, where omega is the matrix multiplication exponent over, let's say, the reals or integers or whatever. But people are not satisfied with these algorithms because they're hugely impractical. So they say, well, we don't want this, we want a combinatorial algorithm. So what is a combinatorial? It's unclear. It doesn't have a real definition, but apparently you know it when you see it. So actually there are algorithms that do not use the big algebraic framework that we have that obtain polylogarithmic improvements over n cubed. And the best such algorithm actually was recently discovered by one of our grad students, Huacheng Yu, and he got n cubed over log to the 4n. This was an improvement over many years. The original 4 Russians algorithm got n cubed over log squared n. So then there's this conjecture that any combinatorial algorithms for BMM requires n cubed minus little of 1 time. So it's kind of a conjecture in quotes because we don't really know what combinatorial is. But it's essentially saying you're not allowed to use subtraction, you're not allowed to, It has to be sort of some data structure stuff, something that seems simple to implement and so on. So this conjecture is then used to prove a lot of lower bounds for dynamic problems and data structure problems and so on. So because it doesn't seem to be using the batch nature of algebraic matrix multiplication algorithms, it allows you to prove things about dynamic things that do things one at a time. Anyway, it's a little vague, but this is another conjecture that people focus on. I'm more in favor of the first 3 that I mentioned. So here's some consequences. So a triangle, if you believe the Boolean matrix multiplication conjecture, then you cannot find a triangle in a graph faster than n cubed minus little of 1 time using a combinatorial algorithm. So in fact, finding a triangle and computing the Boolean matrix product are equivalent under these combinatorial fine-grade reductions. The radius of an unweighted graph requires the same time if you focus only on combinatorial techniques, and notice that BFS and things like this are combinatorial. So you can prove things like this. For also maintaining a bipartite matching dynamically without doing, so the trivial update time, so whenever you remove an edge or add an edge to a graph, in order to check if the graph still has a perfect matching, you find if there's an augmenting path. So that a linear time update time is possible. Doing something better would actually refute the Boolean matrix multiplication conjecture. And really what all of these reductions are saying is that even if you forget about combinatorial, that means that if improving on the runtimes of these algorithms actually requires the use of fast matrix multiplication. So that's what this is really saying. Whenever you get,
So can we replace the 3 minus a little o of 1 with omega?
Not always. It's a good question. So does this imply that Boolean matrix multiplication, so if we get n to the omega minus epsilon, does it imply n to the omega minus epsilon there? No. I mean, sometimes we have a substantial loss, and you'll see this tomorrow.
So when you say combinatorial algorithm, you need some model of computation. So for this to make sense, what's the model of computation? How do you get semantics out of this?
Okay, so suppose I even give you the word arm. I don't even know what combinatorial means, but usually what these reductions do is they partition the input in some clever way. They do some very simple things.
So the reductions, everybody agrees, are combinatorial,
Yes.
and that's it?
Yeah, essentially, there's no formal model, and it's a big weakness of this thing, but it's hard to agree on anything. So we can talk about this offline, but it's difficult.
Have been proposed the lower bounds through, I guess, and word random algorithms to develop which were faster than them.
Yeah, you always, the moment someone builds it, you break it, and yeah, it's difficult. It's unclear. Like I was talking to Ryan and people earlier, because like suppose I have something that works over GF2 and it's just zeros and ones. How are you excluding algorithm, like for example even Strassen over GF2? But isn't that combinatorial? I mean, I don't know. So it's difficult to agree on the model. Okay, so all right. But again, if we have a very simple reduction to problem from Boolean matrix multiplication to problems that roughly preserves the running times, then you say basically these problems require fast matrix multiplication techniques to improve on the trivial algorithm. So another more complicated problem is context-free grammar parsing and so on. So I'm going to talk about for 2 or 3 minutes about this, and then I'll be done. So which conjecture should we believe? Well, there's no other reductions between the conjectures that we know of besides Ryan's proof. It could be that one of them is true and all of the others are false, or maybe any subset of them could be true while the others are false, as far as we know. So there's a few things you can say. So you can look at other models of computation. You can say, well, if you look at the decision tree complexities, then actually there's improved algorithms for 3-sum and all pair shortest paths. So they have much lower decision tree complexities than you believe. We don't really know this for orthogonal vectors, so maybe we should think orthogonal vectors is the most believable conjecture. Sort of a vague intuition. Now, orthogonal vectors and all pair shortest paths admit these wonderful algorithms that beat all logarithmic speedups. But we don't know how to do this for 3-sum. So maybe 3-sum is harder than the other two. We don't know how to discuss this, but what we do know is that there are natural problems that all these 3-sum, all pair shortest paths, and CNF SAT all reduce to. And we had a paper about this. So these are very simple problems about the triangles in a graph, and there's no numbers in the graph. So it's just an unweighted problem. Well, we do have colors. So what is this problem, triangle collection? You have a graph on n nodes. Every node has a color. So, okay, maybe it's order and colors. And now I want to know if the set of triangles hits all triples of colors. So what does this mean? Does every triple of colors, blue, green, red, you restrict your graph on these colors? Whenever you do that, is there a triangle that has all these 3 colors as its nodes? So the triangle collection asks, is there a triangle in every triple of colors? And then there's something, again, matching triangles. Here you're given, again, a graph with colors on the nodes, and a number delta, and you want to know, is there a triple of colors that has at least delta triangles? If delta is 1, then this is equivalent to, is there a triangle in the graph? As delta goes to log n, this becomes hard. So it turns out that you can reduce 3-sum, all pair shortest paths, and k-sat to both these problems, and if you can improve substantially over n cubed on either of these, then all 3-sum has a subquadratic algorithm, all pair shortest paths has a subcubic algorithm, and CNF SAT and strong ETH is false. So yeah, these are the problems you should solve if you do not believe these conjectures. Okay. So we can add these here. Let's say I add triangle collection. We can reduce k-sat, all pair shortest paths, and 3-sum to them. Also, it turns out that you can reduce triangle collection to problems, very interesting problems. For example, maintaining, let's say I want to maintain the number of strongly connected components of a graph under edge insertions and deletions. If your update time is sublinear, then triangle collection has a subcubic algorithm, which means that all of our conjectures are false. So, which is actually strictly, means that that problem is strictly harder. So it's sufficient that one of these conjectures is true for us to believe that dynamic strongly connected components is a difficult problem. So, okay. And there's some other problems related to max flow that they have similar hardness. Okay. So I'll talk about this tomorrow, that on Thursday, and the dynamic problems on Friday. Okay, that's it. Thanks.
One question going back to the very beginning when you were dealing with orthogonal. I was trying to figure out if the square in the as a parameter has anything to do with the dimension of the setting, like K, longest common subsequence, geometry problems, not only polynomials and K dimension.
Oh, I see. So the question is, can we go to n to the k instead of n squared by having a parameter k in the problem? And sometimes you can do. For longest common subsequence, k LCS seems to require whatever n to the k time. And k dominating set seems to require n to the k. So you can do this for some problems. For other problems, it's not as trivial. So for example, for diameter, how do you have to completely change the problem? So there are natural parameterizations of these problems that lead to this.
I'm curious, are there many problems where you reduce two of those three to the problem, but not all three?
Yes. So the question is, are there any problems for which you can reduce two of the problems on the picture to them, but not all three of them? And yes, so there's this problem called exact weight triangle. So here you're given a graph on n nodes, and you have weights on the edges. You want to know if there's a triangle in a graph, so a three-clique, where the weights sum to 0. You can reduce all pair shortest paths and three-sum to this problem, so that a truly subcubic algorithm for that one applies truly subquadratic for threesome and truly subcubic for all pair shortest paths, but we do not know how to reduce CNF SAT or orthogonal vectors to it. Yeah.
Are there any lower bounds under some restricted models for any of these problems?
Yes. So are there lower bounds in restricted models for these problems? Yes, there are. There is a n squared lower bound for threesome for when you're allowed to compare linear combinations of the sums of the numbers, and then you can compare those. Then you require n squared time for all pair shortest paths. There is an n cubed lower bound under a similar model, and there are some things like this.
Do they capture the current best algorithm?
No, because you can get more than polylogarithmic improvements for these, but there's an actually n cubed and n squared for these.
So, is there any evidence you can't reduce SAT to say threesome, like you did for orthogonal vectors?
Yes.
Russ will tell you about this, maybe.
If you this is a recent work with Mohan Paturi and our 4 students who are in the audience somewhere, Marco's there, and others are scattered. So if you believe that a non-deterministic version of the strong exponential time hypothesis, then from that it follows that you cannot reduce orthogonal vector to say threesome or all pair shortest path. Maybe one of the students will talk about this soon.
There seemed to be a reduction. In the reduction to orthogonal vectors, you could go to 3. You want 3 orthogonal that are mutually orthogonal.
Yes.
And is that interesting? Does that give you anything?
Yes. So the question is, instead of just doing 2 orthogonal vectors, you could reduce SAT in the same way to getting 3 mutually orthogonal vectors, or 4, and so on. And yes, you can get reductions from problems like this to some problems. Yeah, but yeah, yes, you can do that. I think these problems, though, maybe they're easier. Orthogonal vectors. You can do it. It's a good question.
So we have this conjecture of this online Boolean matrix multiplication. So there you can get rid of the combinatorial thing at the cost of assuming that online Boolean matrix multiplication. What does that mean? So you have a matrix that's fixed, and then a sequence of vectors comes, and whenever a vector comes, you have to multiply the vector with a matrix. So it's not matrix multiplication, but it's vector matrix multiplication, and it's online. But then you don't need the term combinatorial. But the disadvantage of this conjecture is, of course, that people have not thought about this online version. And so maybe there is a fast algorithm, we don't know yet. But I just wanted to mention this there, that you can get rid of the term combinatorial, and then we can show that various dynamic problems are hard if you assume this online matrix vector multiplication.
But for static problems, though,
yeah.
It's unclear. For dynamic problems, it's extremely useful. But for static, it's
I
unclear.
just wanted to add this in the discussion.
I thought that you would some more do. Okay, I'll mention it actually in another talk.
Fine, I just wanted to mention it, but I mean, I actually encourage the community to maybe come up with a fast algorithm and show that this online matrix vector assumption is wrong. It's just one of these conjectures where even fewer people have worked on.
Thanks, Monica. And I do have more in another talk about this. Yeah, thanks. Yeah.
It was just that point that I know Graham et al. In the 70s had an online method with context-free grammar, but it's actually similar. It's exactly the same. You can apply it to Boolean matrix multiplication. So, and then I know Ryan, his method, the log squared, is also online.
Yeah, so Ryan had a paper on doing orthogonal. So if you can pre-process Boolean matrix multiplication, and then you can feed it vectors to multiply with, and then he can get n squared over log squared runtime for this. And there, Monica et al.'s conjecture is now that actually, no matter how much pre-processing you throw at it, as long as it's polynomial, then the vectors, the matrix vector multiplications require n to the 2 minus little of 1 time. So maybe you can save n to the little of 1 factors, but you're not going to get n to the 1.9. So.
Thanks again.